Thank you so much, and I'm happy to lecture here now. I'm happy. It has been very nice for me to be in Chennai so far. I'm enjoying my stay. So let me start by reminding you what we finished last lecture with. So this was, in some sense, could be viewed as a key construction in intersection theory. And already to define it required some patience. So given f from x to y, a morphism of schemes which are assumed to be of finite type over a fixed field, which admits a factorization x with I a closed regular embedding and pi smooth, then any base change f twiddle so this means that i.e. I'm giving any morphism of schemes and I can let M twiddle be the fiber product and X twiddle in the same way. And this defines for me again a factorization, but now this is still a closed embedding, this is still smooth, but this in general will not be regular. And if it's regular, it may be regular of a different relative dimension. And here I am assuming that f has relative dimension r, which means that pi is smooth of some other relative dimension s, and I is regular of codimension s minus r, r minus s minus r. Okay, so if this all is true, then we have an f upper Schrieg from AD of y twiddle to a d plus r of x twiddle, which commutes with proper push forward, flat base change, flat pullback, and Chern classes operation, where Chern classes are themselves viewed as more maps from a Chow group to another in an appropriate sense. And when we say this, so given a map, then for any base change, we get a morphism on Chow groups which commutes for every d non-negative, which commutes with proper push forward, flat pullback, and Chern classes. And an important way to say this, i.e., by definition, this means that f upper Schrieg, the set of all f upper Schriegs over all base changes, defines a class in what is called, and I think the notation here, you have to decide a sign, and I think the sign convention in the book of Fulton is an minus r of x over y. This is the so-called bivariant class. And this is described in chapter 17. So, do you need the notion of bivariant class? Well, in a sense, no. You could just view it as a short term to say you have a very well behaved pullback. Okay, so first of all, let me remind you that we had one question open, which was what if f is only locally LCI, i.e. such a factorization only exists locally on X. And this is something to which we will go back to at the end of this series of lectures. However, let me remind you how the FA per Schrick was obtained. So the FA per Schrick was obtained by composing a number of steps. So first one went from A dy twiddle to A d plus S x m twiddle, and this was just pullback. I mean, this is flat pullback because every smooth map is also flat. Then one went from here to the normal cone, and this was a so-called specialization, and I will say something about this more in a minute. And finally here one goes to A d plus R of x twiddle, and this step is given by essentially using the fact that C twiddle x twiddle over m twiddle is admits a closed embedding into G twiddle pullback of Cxm, which is a rank R vector bundle. And here what I do is I denote by G twiddle the natural map, the natural morphism, which is induced by saying that X twiddle is a fiber product. So if you want, it's induced by this G. And then what you do is you compose with the inverse of the pullback map. So the pullback from X twiddle to this one, which is just a vector bundle. Okay, so let me recall you one thing I should have said about the specialization, but didn't because I forgot, is that in some sense, so the first thing is a remark. The specialization was defined by saying if I take a V in M twiddle as subvariety, and so I view it as an A-dimensional subvariety, so I view it as an element in the Chow group, then the specialization into A of the same dimension of the normal cone, remember I had defined as the class of the normal cone of W in V, where W is the scheme theoretic intersection of X twiddle and V. And as I was told, I should remember to tell you that another way of seeing this is, remember, we have our degeneration, so we have a flat family. So we have a flat, we have a degeneration to the normal cone, which is a flat family, let me call it Z. I mean, I had different letters last time, but because I was in a different context, over A1, such that, and such that ZT is canonic Z restricted to A1 minus 0 is just M twiddle times A1, and the fiber at 0 is the normal cone. And then what I can do is I can view C, the class of the CW in V, is nothing else but taking V times A1 minus 0, which is a closed subscheme here, take its closure inside Z, and then intersect it with Z0. So in some sense, this tells us that this definition is the only possible one if we want that on the if we want that in the special case where we have X inside E, a vector bundle on X, and then this maps smoothly, and this is the zero section, we want that if we are in this special case, then F upper shriek is the pullback to E composed with the inverse of the pullback from X. And if we want that it varies well in families, so that if we have a family parameterized by A1, then the limit that it commutes well and respects rational equivalence in an appropriate sense. So this is one way. So you could have seen that this is a kind of definition, and you can ask yourself why, and the answer is, well, this is basically the natural way to extend this very special case which we understand. So that in this case is just pullback and intersecting with a zero section. Okay, so let me ask myself, so now you go back to this definition and you wonder which, I already told you that one assumption which we may want to weaken is the existence of a global factorization. However, in the moment from this definition there is no obvious way to do so. However, there is another thing we can do. So let's say we keep the factorization, so closed embedding followed by smooth map. In some sense, I'm not so uncomfortable with this, because typically my idea of a scheme is quasi-projective scheme, and for quasi-projective schemes, a factorization always exists. And let me try to weaken the assumption and look at where did I use that the closed embedding was regular. So here, certainly not. This is just a flat pullback. And also not here, because this is construction is all made for the closed embedding of X twiddle into M twiddle, which is not regular. So until here, I can get with any closed embedding. So what I need is I need to embed this cone inside a bundle. And in this case, I have a natural bundle where to embed my cone, which is just a pullback. So there is therefore what Fulton remarks, and this is Fulton, I think it's called example 17 times 3.2, says the following: assume, and here, remember, so let me tell you the statement. So assume I have a closed embedding X to M. Forget about Y. Together with a closed embedding of cones of the normal cone of X in M inside E, where E is a rank R vector bundle on X. Then, for any base chain, any morphism M twiddle to M, we denote by X twiddle the fiber product as usual, and we can define a morphism which equals IE upper sheik from AD of M twiddle to AD minus R of X twiddle. Sorry? Say it again. Oh yes, sorry. Thank you. Which defining a bivariant class in AR X in M. And how do we define it? So notice the analogy here. We do, well, this step is not there because Y is the same as M, so there's no pullback. And this step here is the same degeneration, and as before, except the last step is we embed C X twiddle M twiddle in G twiddle pullback of CXM. This is a closed embedding, and in turn this has a closed embedding into G pullback of E. And then we intersect with a zero section of E. And then we compose. We have, and then we have, this gives a push forward, gives us a map from A D of C twiddle X twiddle to AD of G pullback of E. And then we have an isomorphism here, which is the pullback from AD minus R of X twiddle. And what we do is we compose with the inverse. So in some sense, one of the reasons why Fulton writes this example is because he wants to show you that there are other equivariant classes. I mean, just that the definition makes sense, and in fact, All you needed to make the definition work here, at least if you don't worry about the smooth map part, but just look at the intersection with a closed subset, which is after all, again, why it's called intersection theory. You have a cycle class here and you want to get a cycle class there, so you are really intersecting. And what he says is, I don't quite need a regular embedding. All I need is a choice of a closed embedding of the normal cone inside E. Notice that this will depend on the choice of E. If nothing else, because if you have any given E, you can always direct sum some other vector bundle and get something bigger, which will then give you a morphism of lower degree. Let me so remark, so these are all also immediately after this. Remark 1 is, of course, this depends on the choice of E, and this is kind of obvious. And the second is we can use what we know about cones to express this condition differently. So to give CXM in E, well, remember that giving a morphism from a cone to an abelian cone, so one which is just a spec sim of a sheaf, is the same as to give a morphism from the associated abelian cone, and the surjectivity condition is the same. So this is the same, and the next step, because basically this what you can check is that this is equivalent to E surjects in I mod I square, where E is spec sim E, and I is the ideal sheaf of X in M. So certainly if this is a closed embedding, then so it is this, because this is a closed embedding in this one. But on the other hand, to have a closed embedding corresponds to having a surjective morphism of graded algebras. And if it's surjective, if and only if it's surjective in every degree, and in degree 1, this is a spec sim E, so the degree 1 part is E, and the degree 1 part of this one is I mod I squared. So this tells you that in either case, this surjectivity is what counts. So in other words, we get that so long as we take what we would like to call the conormal coherent sheaf, so something which is actually a sheaf, and we find a locally free sheaf of finite rank surjecting on it, we can do a pullback. So let me ask one more natural question at this point, actually two more natural questions. And we'll see how answering these will eventually also lead to an answer to this question here. So two more natural questions. Well, the first question is, in some sense, what happens is that Fulton could really have put this directly after defining F upper Schrick like I did. So why didn't he? And I think the point is that he didn't really have a good example. So the first question is, how do we apply the lemma? So where do we get, given a closed embedding, where do we get a vector bundle in which the normal cone embeds, or equivalently, where do we get a local, how do we check this assumption that we can, what is a good condition that it would come up in our natural mathematical life, that there is such a surjective morphism. So that is, you know, find natural applications. And then there is a second question which has a more, so to speak, philosophical nature. So if you look at how this definition is given, and in particular if you look at how, in which order things are proven in the book of Fulton, what happens is you notice that you go in several steps. So what you do first is, first of all, you prove that if I is a regular closed embedding of codimension R, then you get a class I upper shriek in A R of X to M. So this is kind of the first step, the case where we already start with a closed embedding and we work with that. And then this has two generalizations. On the one side, we have I, a closed embedding, plus an embedding CXM inside E, and you get I, E upper shriek, also in A minus R. And on the other hand, we also have a generalization in the other direction, that if you have F is equal to I composed pi, pi composed I, LCI of relative dimension R, then you get an F upper shriek in A minus R of X to Y. This is plus R, where E a rank R vector bundle on X. Okay, so then so I've started with a special case, I mean a very important special case. This, I think, is what is called the generalized Gysin pullback, or maybe Gysin pullback, generalized Gysin pullback. And you generalize in two directions. One is you compose this with a smooth map and show that the result only depends on F and not on the particular choice of factorization. And on the other side, you say, okay, I can weaken my assumption. I start not with a regular closed embedding, but just with a closed embedding. And I, you know, instead of having a vector bundle by definition, because it's a regular closed embedding, I choose one, and then I still can do it. So my question is there a way to generalize these two simultaneously? So can I find something that plays the same role, that in some sense, so what would I mean here? Basically is, in other words, what assumptions do I need on, so, well, not assumptions, but let me actually write this better.
So for every choice of E, you can still take the composite of pi with that and ask what's happening. That's what you're saying.
Yes. So my question is, what do I, let me say it better. So here you see that for such a thing I have a bivariant class is kind of obvious, because smooth morphisms are bivariant, pullback by a flat map, so in particular by smooth is bivariant, this is bivariant, composition is bivariant. So that's very easy. So here the non-trivial result at this point is that this only depends on F. and not on the choice of factorization.
Because you have given a God-given choice of the vector modeling.
Sorry?
You have given a choice of vector modeling because
Okay, let me come to this point here, and then you can ask your question after I finish the next sentence. Yes.
Which one is that? Minus upper minus R or lower minus R?
upper minus R is
So the point is that
Not there.
oh yes, sorry, this is R and this is upper. This is always upper. Thank you so much. This is, and the point is that the index here is given since he's mostly using it in this case. Then he wants a positive index when the dimension goes down, which is also natural, because what you should do is think of this as a cohomology, and cohomology lowers homology degrees and not raises it. Thank you so much. Okay, let me just say what I want to say here. So what I want to know is so here I started with regular closed embedding. I removed the condition of being regular and I added a bundle. Here instead I took a morphism and I assume it has a factorization, but I didn't choose one. So how do I do a common case? What I would want to know is what additional structure do I need on an x to y such that for any or for some factorization x I m pi y, where this is now just closed embedding, no more Legora, but this is still smooth. There exists an induced embedding Cxm into E such that P upper shriek composed IE upper shriek only depends on the data on this additional structure and not on the choice of factorization. So, does this answer your question?
Yeah, but the choice of E will of course make it different each time.
No, but what I want, see, here I had no choice, and also here I have no choice.
So you have a canonical choice.
Okay, it is built in. Here I have a canonical choice, and here I have a canonical choice. Here I'm choosing an extra data. What I want to do here, it's clear that if I choose such a thing, I get it. But what I want is I want something which I can choose already at the level of the morphism x to y without choosing a specific factorization. So here what was non-trivial in this step is not that to a factorization I can associate a Bavarian class, which is obvious. I mean, once you believe this, but once you believe this is pretty obvious. But what is non-trivial is that the Bavarian class doesn't depend on the factorization. The fact that I didn't give you the details of the proof doesn't mean it is a completely trivial proof. All you need, however, was, if you remember, there was an exact sequence of cones. And I asked you to believe me that this exact sequence was all you needed. And I think I would need at least to use a whole lecture on cones and fundamental, Segre classes of cones and so on to check that this is actually true. But since it is all written in the book, I suggest you believe me and we move on to doing this step instead. So here what I want is to kind of parallel this step. So again, it is clear that if I choose a factorization and I choose such a thing, then I have a Bavarian class. The question is, what can I do already at this level, which will not depend, will imply that I can do such a thing and will not depend on which one I choose. So let me rephrase this.
So to get rid of the vector bundle independent of the factorization, is it?
Well, the point is the vector bundle, let me tell you in a moment which property I want, because this is actually an important thing. Only I tend to, maybe on this, in this room I could write a bit smaller, because after all, it's not as deep as the room at, so if I wrote smaller, I wouldn't have to erase so often. Anyway, so i.e., what do I want? Remember, how did we compare two factorizations? We took one factorization and we compared it to another, which had the following property. We need, remember, recall, to prove this fact that this only depends on f. What we needed was that given such a diagram with I, J closed embedding and rho pi smooth, what we needed is that there exists an exact sequence of cones 0 to J pullback of T rho to the normal cone of X in M to the normal cone, in P to the normal cone of X in M, induced by an exact sequence of coherent sheaves, abelian cones, and abelian cones, remember, are the same as coherent sheaves with arrows reversed. So let me write it in the coherent sheaf case. 0 in I mod I squared in J mod J squared in J pullback of omega 1 rho, where I is the ideal sheaf of X in M and J is the ideal sheaf of X in P. So I didn't tell you how, but basically this was, the good point was that once you have this sequence for X in M, remember that we had our M twiddle and everything got twiddled, and then I took a variety inside M twiddle. But the point is, if I base change such a diagram with any morphism to Y, it still is exactly of the same property, because being smooth and being closed embedding certainly don't get disturbed by taking a fiber product. And then what I can go is I can do one more step. I take something which maps to V, which is reduced irreducible. And then if I take the pullback via P, it's still reduced. Well, it may not be irreducible, but then it has a irreducible connected component, so I do it component-wise. This is not going to be a problem. And the normal cones will again satisfy such a sequence. So this is really something very basic and very crucial. So what you want is that if to this factorization you want to associate a bundle which depends on this closed embedding here. So let me assume I'm in the case where for any factorization, but again it would be enough that there is some, and then I can compare any two on which I have it with a third. So assume, and then I can compare both with such a thing. So assume we are given, so on this one, I have an E surjecting EI, surjecting on I mod I squared, and I have an EJ surjecting on J mod J squared. Then to get the correct result, what I need is, so here I have EI, and here I have EJ. And what I request is that this sequence, there exists a natural morphism here such that so what I want is that there exists this and there exists this such that this diagram has is commutative and has exact rows. So what I want is for some choice of factorization, or for all, ideally, choice of factorization, I want such a thing. And whenever I can compare two factorization, I want such a natural map. So I have, you see, in some sense, I have two different questions at the same time. So one question is something about existence of sheaves and morphisms. So what I want is for every factorization, I want a sheaf mapping to here, such that when I have two compatible ones, there is such an exact sequence. And then somehow independently from this, there is the condition that this be surjective. Of course, by the usual, since these are all sequences where the right-hand term is locally free, hence this is locally split. Once I have a commutative diagram and this row is exact, then surjectivity here is equivalent to surjectivity here. So I have, in some sense, what I could decide is to reverse the procedure. First, I want to find a compatible way to put all these E's, and then I will worry about how to check that for one of them, and equivalently for all of them, this thing here is surjective.
So you want to choose the EJ before itself, is it?
Say it again?
The EJ, is it chosen a priori, or you can always choose it later?
Well, the point is, what I want is I want to find something which is only defined here, which then whenever I choose a factorization will provide me with such an E. So what I want is I want something global, which I can define directly on x to y and without choosing a factorization, and on which basically carries the information of each of these I mod I squared. But recall, I had told you we had one object which was globally defined, which was an element in the derived category. So what we had seen, so recall, given a factorization of f, the morphism from I mod I squared to I pullback of omega 1 pi, remember this had the property that its kernel and its co-kernel did not depend on the factorization chosen. Its kernel and co-kernel. The co-kernel, by the way, is omega 1 xy, do not depend on the factorization. And the kernel and the co-kernel of a morphism are very natural conditions, but if you have ever seen the definition of derived category, then what you get naturally is that i.e. the complex 0, 0, all zeros, the infinitely many zeros. And then I have a 0, I mod I squared, I pull back of omega 1 pi, 0, all zeros. So this is an infinite complex, but with only two non-zero terms, is unique up to canonical isomorphism in the derived category of coherent sheaves on X. So, so what is the formal definition of derived category? Let me give you a crash course. This will be boring if you know it and useless if you don't, but it's supposed to give you a motivation. So just at least get familiar, and if you don't know it, we will work this baby case, which will turn out to be much simpler. So in general, if A is an abelian category, and if you don't know what an abelian category is, it's no problem. Just think as sheaves of OX modules or things of quasi-coherent sheaves, or think of coherent sheaves. Then you define C of A to be the category which objects are complexes, so objects and maps such that the composition of two maps is 0, and morphisms are chain maps. So morphism grade-wise, so this is AI to AI plus 1 to AI plus 2, indexed by the integers, and the morphism are graded maps which commute with the differentials. And then what you do is for such a morphism, you can, to such a morphism, if you have f from A dot to B dot, this defines you a morphism which you call hi of phi from hi of A dot to hi of B dot. Because since it commutes with the boundary maps, it sends cycles to cycles and boundaries to boundaries, and so it sends cohomology to cohomology. And you say that phi is a quasi-isomorphism. So notice I will always write it like this because I'm lazy, but this is quasi-isomorphism, I think with a hyphen, but don't quote me on that. Even only if all hi phi are isomorphism. So the idea is that in some sense for complexes, what you really care about is not the complex itself, but the information carried by its cohomology. And so these things here are moral isomorphisms, and then you define D of A dot as by a universal property to be an additive category. Additive category just means that the morphisms are groups and the composition behaves. Together with a functor from the complexes. So this is A. These are all my attempts to have curly A's. Such that quasi-isomorphisms map to isomorphisms, and it's universal with its property. So for any other map such that quasi-isomorphism map to isomorphism, there is an essentially unique factorization. So universal with this property. So an informal way is to say you are inverting quasi-isomorphisms. Now, what happens when you, and by the way, I think the derived category is possibly one of the very few important topics in algebraic geometry which is not in the book of Hartshorne. And so I suggest you familiarize yourself, if not with the proofs, at least with the arguments. For instance, one use of the derived category is you get a much more understandable definition of derived functors like cohomology. Moreover, once you have the language of derived categories, when you study Hartshorne, in chapter 3, section 7, when he defines X groups, he goes out of his way to tell you that despite appearances, X is only a derived functor in the first variable, but not in the second. And once you generalize the notion of derived functor using the full power of the derived category, it turns out that X is actually also a derived functor in the second variable. And in fact, you can define more defined derived functors which are not there in the book of Hartshorne for the very good reason that the correct assumption in his framework would be you need to have enough projectives, and basically you never have enough projectives in a category like this unless X is affine. But what you do when you work in derived categories, you can weaken this assumption, and so you get derived functors, for instance, for pullback or for tensor products, which are extremely useful. So if if you are not familiar with the derived category, learn it today. The other reason you may want to learn derived categories is they are extremely important object of study for their own sake, and I certainly know at least one paper by Kawamata nonetheless, where basically the beginning, the first sentence of the paper is assume that X and Y are projective manifolds which define the same physics, namely they have isomorphic derived categories. So if this doesn't sell derived categories to you, I don't know what else can. But for that matter, let me do the following baby case. So let me consider now d minus 1, 0 of co-X, and this is supposed to be the full subcategory of d co-X of complexes where the objects are complexes A dot, let me call them F dot since they are coherent sheaves, such that Hi of F dot is equal to 0 away from 0 and minus 1. So what I have is let me give you an alternative description of this category, and let me assume for simplicity that X has enough locally frees. And enough locally frees, this you can find it in Hartshorne. It means that every coherent sheaf is a quotient of a finite rank locally free sheaf. And this in particular is true if X admits an embedding, a closed embedding into a smooth scheme. because it's true if X is a smooth scheme, and if you have a closed embedding, coherent sheaves on the closed subscheme are a subcategory of coherent sheaves on the ambient. So e.g. X quasi-projective will be enough. Okay, then there is a natural category which gives me a map to the category of complexes which have only 0 and -1 cohomology. So I can make some stupid category, let me call this B, because this will turn out, because this will not be quite a category in the end. So let me define a category B for baby example, where the objects are morphisms D from F-1 to F0, morphisms of coherent sheaves on X. And the morphisms are the commutative diagrams. A morphism from F-1, F0 to G-1, G0 is a pair F-1, F0 such that the obvious diagram commutes. So this is an obvious category, and certainly there is a natural mapping from B to the derived category -1, 0 of cox, where I take an F-1 to F0 and make it into a complex by just adding zeros before and after. Notice that in all this picture, I could have chosen any two numbers next to each other in the list. I could have taken 3, 4, but you know, this is in some sense this is the natural choice, as we will see later. So what we have is, this is clearly, it's what is easy to see is that this is essentially surjective. This is so easy. This is essentially, actually let me do, this is essentially surjective, but of course it's not an equivalence, because here in general, even if I have such a phi, it is not a priori such a phi such that it induces a quasi-isomorphism, which means induces an isomorphism on the kernel and isomorphism on the co-kernel. It is not an isomorphism. So this is essentially surjective, but not an equivalence. There is something which is not quite as easy, but not so bad, not too difficult. The same is true if we insist in the definition that the locally free sheaf, that the sheaf in degree 0 not only be coherent, but be coherent and locally free. That F0 be locally free of finite rank. Some finite rank, I can't fix it, but of a given finite rank. What you have is you have your F0 and F-1, and here you have an E0 which is surjective. These always exist, so here you assume that Fi are both coherent, and then since there are enough locally free, there exists such a surjection with A0 locally free. And then what you do is you define E minus 1 to be the kernel of the natural map from f minus 1 direct sum E0 to F0. And what you show is, of course, you get a commutative diagram E minus 1 to F minus 1 to E0 to F0. And of course, to get this diagram, you have some choice of sign. So this, let me this be a warning to you. Any text in derived category has two options. Either be very precise about the sign or get the sign wrong. In some case, both options in the same text. So beware if you are the kind of person like me. I mean, I studied Griffiths-Harris assuming that 2 pi I was equal to 1. It simplified formulas excessively. But if you are bothered by signs, as you should be because you're not me, then beware that some of the most reasonable texts have occasionally the signs moving around. So just know this, that usually a good suggestion is first you read it trusting that the signs can all be fixed together, and then if you really need the stuff, you go through it and check that all the signs work. So here it's clear that to get a commutative diagram, I will need to choose one of these two maps with a sign so that this gets reasonable. Okay, and then what you prove is that this is a quasi-isomorphism. So it induces an isomorphism on kernel and co-kernel. In particular, this tells you that it's still true that it is essentially surjective, because each object which comes from here is equivalent in the derived category to an object where this F0 is locally free. And moreover, a priori we don't know this, but what we have seen is that if x y has a factorization, then to each factorization we can associate exactly such an object. Omega rho, omega m in y, which is an object in B with this one locally free. So we are really in the simplest of simplest cases, and changing the factorization gives me a diagram like this, which is well known to be an of quasi-isomorphism, which therefore defines an isomorphism, a natural isomorphism in the derived category. So this is the situation. So what are we going to do with it? So this is the natural object. This is the object which is defined. If you view this as element in the derived category, then this object is well defined in, does not depend on the choice of factorization. Okay, so now let's go back to what we wanted. So remember, what we want is such an exact sequence, or in other words, we want a compatible condition equivalently a condition on abelian codes. Yes? So to each factorization, we associate an object in B.
Why is it independent of the factorization? In B itself?
No, I said in B. And then what I just said and didn't write is that such that it defines an object in D minus 1, 0 co-X, which is unique up to canonical isomorphism. So to each factorization I get an object in B, and then I have a map from B to this guy here, and it's the object here which is canonical. Okay, so you ask yourself, okay, yes, of course I could write this in terms of coherent sheaves or in terms of abelian cones. And how does this help me any? You know, I don't know how to generalize this here either for sheaves or for cones. Well, let me tell you that there is in fact an important special case of this whole story where you actually understand what is going on, which you remember is the case where this x into y is actually a closed embedding. So if x into y is a closed embedding, what you get, remember that here the co-kernel is omega of x over y. So if you want, in fact, all that is important is that this map is unramified, which means this omega is 0. Then the condition of being a quasi-isomorphism, etc., is just something about the kernel of this map, because the co-kernel is 0. And so what you get if omega xy is 0, e.g. if x has a closed embedding, well, then we really understand what's going on. But then what happens is that we have something which has no cohomology in degree 0. So what we are doing is we are working with d0, d minus 1 of co-x. So if you want is d minus 1 minus 1. So it means this thing here is supposed to be the interval where the non-zero cohomology lives. And in this case, there's only one non-zero cohomology. And it doesn't matter which one you choose. This is always this has a map, which is h minus 1 to co-x. And this is an equivalence of categories. This is one of the first things you prove, that if you take any abelian category and you take the derived category of complexes which have cohomology concentrated in a degree d, whatever the d, then taking the dth cohomology is an equivalence. So insisting that your complex has cohomology in 1 degree just means you don't have to do this whole rigmarole. So in other words, what you get is that if you insist the reason, so if you want to be philosophical, the reason why this argument of Fulton, like why 17.3.2 works, is that if you insist that you have complexes in degree, only 1 degree, they have a geometric counterpart, which is the abelian cones, which then you can work with geometrically. Now, at this point, if you were me, you would be as ignorant as you were before, because you say, okay, here I understand everything, but here I don't, so what? But if you are the kind of person who, for his own pleasure and education, reads papers by Deligne, then you would be extremely familiar with Exposé 18 in EGA, and I think in SGA, and I think it's 4.5. And let me insist, sorry, this is of course spelled big. Let me insist that it is, I think it's 4.5, it might be 4, anyway, one or the other. And there, it turns out that Deligne constructs something called Picard stacks. So this is I don't remember the title, it might be Champ de Picard. Oh, of course, just to make things easier, it's in French. Now, if you're Italian, this is not the least of your problems. This is just the fact of life. But the translation of the title is Picard stacks. And in this paper, the ligne proves the following. So the ligne defines Picard stacks over, I think, an arbitrary topological space with a over an arbitrary category with a Grothendieck topology, and shows over, I think, if one way to say it is over a topos X or over X, but for us, let's take X a topological space, but in fact what we really will eventually want is the more general definition. But say e.g. For X a topological space, what he proves is that there exists a natural equivalence of categories from D01 of abelian sheaves on X, and when I underline something, it is to tell you that in Hartshorne this would be a fractua, so these is Gothic letters. I can't draw the Gothic letters. So if when in the lecture notes you may want to use mathfrac. To the homotopy category of Picard stacks. So this will be the hardcore part of this second week. And so my purpose now in the quarter of an hour that we have left is to give you an idea about what this is supposed to mean and why this is supposed to help us. Questions?
Is there a reason you now go from -1, 0 to 0, 1?
No, it's just that this is the degrees that the ligne has. So I want to make sure that I write exactly his statement. And my first next step, it is a bit complicated. So let me start by saying this is the notation the ligne has, but it will turn out that actually we will also go in that direction because we are doing something a bit more complicated. So what you could say, of course, this is not going to help you very much because you don't know what a Picard stack is. You don't know what you mean by homotopy category of something, or maybe you do, maybe you don't. And in any case, you are extremely unhappy. So I was into something which I barely understood, and now I waded out into something which is completely abstract, and moreover it's in French, in every sense of the word French in algebraic geometry. So let me start by giving you a name. Of course, this is now whenever I hear it, I always think of Captain Picard of Star Trek. But this is not what the ligne did, because this paper actually is from, I think, 1974. So I could have read it in primary school. What the ligne means is the following. You all know that line bundles over a, say, smooth projective variety are a scheme, the Picard scheme. But if you try to write down what is the universal property of the Picard scheme, so what, if you want to write this as a scheme that represents a functor, you have to do this wild trick with the tensor. So remember that if V is, say, a smooth projective variety, then pick V is the scheme that represent the functor from schemes up to sets which sends S to L in peak V times S modulo an equivalence relation where L1 is equivalent to L2 if and only if there exists an M in peak S such that L1 is isomorphic to L2 tensor P2 PS fullback of M. Now, if you are most normal people, you will be very happy. This is a clear definition. At some point, you will understand it and you will feel very smug. But if you are Deligne, you are bothered. What is this M doing here? And you would like to say, you know, I don't want to kill the isomorphisms. And if you are Deligne, you are of course familiar with the theses of Grothendieck's students before you. And in particular, you are familiar with the thesis of Giraud, who defined what he called champ, because the Frenchmen, you know, don't use field. This, of course, means field. And French don't call field, but they call it corps, so they, which means body. And so this confused notation forever. So this means basically nobody in this English-speaking world wanted to look at this stuff until Deligne and Mumford came and decided to call them stacks. So this is the French, and this is the English. And by the way, this is also the Italian. Nobody ever bothered writing a translation. So now you have learned your first Italian word. Okay, so what Giraud did is he basically answered this or this. Answered is a sheaf of groupoids. And I will not give you the definition, after all I have written a short paper about this, but let me just remind you that a groupoid is a category where all morphisms are isomorphisms. And in particular, this has usually when you have categories have categories, then there are functors, and then there are natural morphisms of functors. Remember that if C1 and C2 are categories, and F and G are functors, and in my here functors will always be assumed to be covariant. When I need a contravariant functor, I just change the arrow, the direction of the arrows in one of the two categories. Then I know that a natural transformation alpha from F to G is the datum for every object, let me call it X, object of C1 of a morphism from X, from F of X to G of X, such that for every morphism F from X to Y in C1, the diagram F of X to G of X, F of Y, F of F, G of Y, G of F, alpha X, alpha Y commutes in C2. This is a morphism in C2. And the natural transformation is called the natural equivalence if all these alpha X are isomorphism. And of course, one good thing is that if you insist that you don't look at arbitrary categories, but you look at groupoids, then every natural transformation is automatically a natural equivalence because all morphisms are isomorphisms. So in particular, what this tells you is that groupoids are naturally a 2 category, a very well behaved 2 category. And again, I can give you a reference for what it means to be a 2 category, but I don't suggest that you run and look at the definition. I suggest that you start by getting an intuition of what's going on. Basically, let me write down what I mean by this in pictures. When you work in a category, you are all familiar with the notion of commutative diagram, and now what you need is a 2 commutative diagram. So you have C1, C2, F, G, and alpha. So commutative diagrams in a 2 category are surfaces. And a 2 commutative diagram will be like the surface, typically will be the surface of a solid, and you have commutative diagrams or 2 arrows on all the faces, and you have a compatibility. And the hard part of writing this all down is that you don't have a 3-dimensional sheet of paper, so you have for every such solid to find a clever way how to write down the corresponding to commutative diagram. And now we start hopefully seeing some light. So the first thing is, in what sense are stacks generalizations of sheaf? So let me try to make parallels. So you have that sets are related to groupoids. How are they related? Every set is a groupoid if you take the points of the elements of the sets as the objects and the identities as the maps. And if you have this kind of proportion, then you get that the sheaf of sets it corresponds to a stack. So this means that if you have a stack which is a functor, a sheaf is a functor from the open subsets to the sets with a contravariant functor with some gluing property, and the stack is what is called a pseudo functor because it goes to a 2 category. There are usually 2 different notion, which is pseudo functor and lex functor, but since we are going to groupoids and not to arbitrary categories, they are the same, so you can use whichever one you like. And a stack is a special case of pseudo functor to groupoids on opens, such that it has a gluing property, and if it goes into groupoids which are equivalent to sets, then it is actually a sheaf. So this is really a proportion. And now what happens once you understand all of this, then what you get is that the sheaf of abelian groups correspond to Picard stacks. And let me write down for you which one I think is the point which I found difficult to understand when I read it in the paper of Deligne. So let me tell you the one thing which is not written, not because Deligne didn't know it, but because he found it so easy that he couldn't be bothered to write it down. So let me assume that before if you want to generalize things, you would think that going directly at this step would be a bit of a tall order. So let me say how I generalize abelian groups to something here. So something here, for instance, if you want, it's Picard stacks over a point. So remember, what I want to do is, if S is a set, I associate to it a groupoid S where the objects are S and the morphisms are all the identities. So how do I say that a set is a group? Well, we all know the definition. To say that the set is a group means that you have a multiplication map from S cross S to S, and an identity element from a point to S, and an inverse from S to S, such that a number of diagrams to commute. In particular, what we want is that x times y is y times x, and then that e times x is x, and then that x times x minus 1 is e. So this gives you 3 commutative diagrams. I mean, I could write them for you, but you can write them yourself. And when you want to generalize this on the groupoid stack, every commutative diagram gives you a 2 arrow, because usually there will not be natural on-the-nose commutations. So you will be left with 3 2 arrows. And you are very unhappy out of this, because 2 arrows are expensive, and every 2 arrows will give you some horrendous diagram, and you don't want them. So what? Oh yes, and sorry, 4, because there's also the associativity, right? It's a group. So what is the nasty trick of the Ligne, which he doesn't tell you? Nasty trick is the following lemma, to give a set S an abelian group structure is equivalent to give a multiplication which is commutative, associative, so you still get the first 2, and then there comes the nasty trick, and for every S in S, the multiplication with S, which is a bijection. So this is something that you could give a first-year algebra student as an exercise. It's a nice exercise. And the point is, once you have this, what the Ligne does is he replaces the bijection condition with being an equivalence of groupoids. Bijection is an isomorphism of sets, so this becomes an equivalence of groupoids. And then he gets only 2 arrows in the picture, which corresponds to the commutativity of these 2 diagrams, and then he writes one big diagram, or actually 2, which tell you everything you need to know about how these 2 arrows behave well. Basically, what you need is you have an associativity at 4 level, you get a cube, and each side has a 2 arrow, and you want that this whole cube commutes. And then there's a similar condition on the commutativity. So the point is, that is the basis of the definition of Picard stack. When you define a sheaf of abelian groups, do you need to be smart? Well, it depends. You may need to be smart the first time, but once you have figured out the definition of sheaf and the definition of abelian groups, putting them together is pretty trivial. And also putting these together is exactly as trivial. So what you ask is that a stack is a functor to groupoids. What you want is that this functor is in fact a functor to these groupoids with this additional structure, and that all the restrictions commute with this additional structure in the natural sense. So in some sense, once you have, so if you split this problem, you see that what you're doing is you are defining 2 difficult things. This one, which is difficult, but it was done by Giraud, and this one, which is in some sense very, it still takes an effort, but it isn't terribly difficult. And in fact, it turns out that this object here.
So you can interpret, how did you categorize for every S?
So what I'm saying is that the definition, and let me be very imprecise, is a groupoid a Picard stack over a point is self is a Picard groupoid. Actually, why don't I call it Picard groupoid? A Picard groupoid, and with this I'll be finished. A Picard groupoid is a groupoid together with morphisms. Let me call it G underlined, and again this should mean you could have it meth-rec or maybe meth-cal, some notation. Together with multiplication map, this is just the product of category, so two objects and two maps. And
This doesn't have any two categories.
These are two categories because, of course, this is the definition of one. This is a groupoid with such a thing and such that, and two arrows. Two arrows corresponding to associativity and commutativity, such that, and there are compatibilities of two arrows, and then there is the condition that for every object the multiplication by the object is an equivalence of groupoids, and for every G object the multiplication by G is an equivalence of groupoids. So this is the generalization to groupoids of abelian groups. So you have that sets is to groupoids as abelian groups is to Picard groupoids. And the point is, what I will not say, because of course I'm saved by the bell, is that these, like abelian groups, have a category structure, which is a subcategory, but certainly not a full subcategory of sets. So Picard groups have a two-category structure, which is a subcategory, but a sub-2 category, but not full sub-2 category of the category of groupoids. It's actually not really a sub, it's just something else. Okay, so it's just that you have a two-category structure on this, and then you put this and this together, and you get a definition of Picard stack. And in particular, afterwards, Deligne proves that if you associate to every scheme the groupoid of line bundles on V times S as a groupoid, so up to isomorphism, forget the tensor, you get a nice stack. And this stack is actually, will eventually become algebraic, but it's only algebraic, not with a definition of algebraic. Deligne gave more or less with a definition of algebraic stack given by Artin also the paper is from 74, but I'm sure Deligne was familiar with it earlier, so he knew that this was going on. So what you get is this, this way you really associate to a geometric object. So what you have here, you have from abelian groups, you can find a geometric counterpart, and for sheaves of abelian groups, you can find also counterpart with one level more of category, so to speak. So where the thing is not a category but a two category, and this is the natural equivalent. And what we will see is that we can keep going on. Now we have that, and what Deligne proves here is that these Picard groupoids, the Picard stacks, luckily I still have it here, correspond to the derived category of the category of abelian sheaves. And so what happens here is now we have a natural generalization of this. If you want, you can have vector spaces, and you can try to put something here. And then what are sheaves of vector spaces? These are coherent sheaves. And then here you get what is called abelian cone stacks. So this is the abelian cone stacks. But this, forget about the name. What we have there, I didn't also tell you what is given here. So if, in some sense, both are abelian cone stacks, except these are abelian cone stacks over a point. But the point is you are just copying this definition, except now you have to decide which definition of a vector space you are going to get, because as I told you, one way the Ligne got a manageable thing was by tweaking the definition of abelian group, which you think there would be only one way to write it. And the trick is always to write a definition with as few commutative diagrams as possible. Because every commutative diagram is a two-arrow, you will have to drag along every definition you give. So the least you put in, the happier you are. So this is the situation, and this is what we are going to see either tomorrow. I'm still kind of deciding in what order, because this is pretty heavy material, but it might be that tomorrow we take a break and we do a little bit of deformation theory before going back to this nasty stuff. But just so that you have a bit also of time between now and Thursday to read again this stuff, and if you have questions, you can ask them anytime I'm here. Okay, so this is it for today. Thank you so much.